This experiment done by ChemToddler is the most stunning chromatography experiment on the internet. It uses thin layer chromatography and a ultraviolet light. Thin layer chromatography uses plates, aluminum or glass, coated with a silica gel. You're probably more acquainted with chromatography paper that's made out of cellulose fibers, basically plain paper. Students generally use chromatography paper for their first experiments because they only cost about 40 cents a sheet, while TLC plates are $8 a sheet, so it's not best for a first try for chromatography. These TLA sheets are aluminum or thin glass sheets that are coated with a silica gel. The silica gel is silicon oxide, basically mini glass beads and nanometer scale. The gel is used for an amazing number of things. It's found in kitty litter because it absorbs a lot of water. If you have a box or a package that needs to be kept dry, there'll be little packets of silica gel in it that are used to absorb the water. In this case, the silica gel is used to absorb the solvent. Here we've got an electron microscope picture of these little glass beads that make up the silica gel. And here you see 60 billionths of a meter would be the scale of the beads and the spaces between them. The solvent that is used and the analyte, now dye molecules, they're about a nanometer across. And if the solvent molecules are smaller than that, if I get these things to the right scale, I'd have to make this down to 1 nanometer. So you can see the solvent and the solutes are going to find a lot of room in between the spaces. So these gaps are huge compared to the solvent and even these large dye molecules. Let's look at what's going to happen on a molecular scale. These are huge beads that are coated with silica, which has OH on it, which is very, very polar. Hydrogen bonds, oxygens with a negative, and you've H pluses. So the silica is a very polar substance. The solvent can be a mixture. In this case, they've got some ethanol and acetone, which will have some attraction to the silica gel, enough so that the small gaps in it will cause capillary action, and our solvent will move up through the silica gel. So you'll see the solvent moving up, and our analyte's going to end up having a choice to make. Here we've got our silica beads glued onto the aluminum foil backing. That analyte, if it's very, very polar itself, end up sticking to these beads. The solvent will keep on moving, and the analyte will be stuck to the silica gel. But if the analyte ends up having attractions to the solvent molecule, so the analyte will move with the solvent as it wicks up using capillary action. So we're going to see a battle. The analyte is being attracted to the solvent and moves with the solvent, or if the analyte is attracted to the fixed silica gel and stays with the silica gel as the solvent front moves. So we've got this experiment up. Let's see what happens on the macroscopic scale. One of the reasons this experiment is so spectacular is because it uses fluorescent dyes. While fluorescence itself isn't part of AP chemistry, the principles involved in it are. The first principle is that we're dealing with a black light, which is really ultraviolet light. It's got a short enough wavelength that we can't see it. This short wavelength ultraviolet light is bombarding the dye. Now, the electrons in this dye will absorb this photon. The principle in AP Chem is that if a photon is absorbed by an electron, it becomes excited, and it moves to a higher potential energy level. This invisible photon is absorbed. We move up to an excited, higher potential energy. Now, these molecules are such that once they absorb this energy, they'll undergo some molecular motion, and that motion will lower the potential energy of that electron to a spot where when it drops from this level, it emits a photon. This is basically, it absorbs a photon, it loses a little bit of energy, and then drops down to a lower energy level. But because it's at a lower potential energy, this photon has a longer wavelength and is visible. So you've got this invisible light that kicks an electron up. The electron moves down just a little and then drops down, giving us the visible light. That's the fluorescence. Now, this happens within nanoseconds. Fluorescence explained using the principles in AP chemistry. Fluorescence isn't just for looks, it's a powerful tool. It's easy to spot photons. They can be detected down to single photons quite easily. The amounts of material in these dyes and these vials is tiny, tiny, tiny. We couldn't weigh them, but we can see them because of this fluorescence. So using fluorescence, we can identify even parts of a DNA molecule. It's a powerful tool that allows us to measure the smallest of amounts of substances. Let's look at the molecular structures of these compounds. We have rhodamine B, rhodamine 6G, and 9,10 diphenylanthracene, and of course the mixture. The first we'll look at is the rhodamine B. One thing that's common with dyes and these fluorescent materials is that they have alternating pi bonds. These alternating pi bonds can be excited by visible photons and even ultraviolet photons and will produce these spectacular colors. You'll see this is common in all of our dyes. Rhodamine B has COOH, so it's going to have hydrogen bonding, and we've got some strong ion charges here, so this is going to be a very, very polar substance. Rhodamine B, soluble in water, which we'd expect because of this OH, similar intermolecular attractions with water molecules. This is going to be attracted to anything that's extremely polar. Now let's look at our next compound. Well, here we've got our brilliant rhodamine 6G. It's this yellow color. It's got our alternating pi bonds all around it. It has two amine groups, this NH, so it's going to have some strong hydrogen bonding, and this is soluble in water too. Our rhodamine G, pretty polar substance also. Now to our 9,10 diphenylanthracene. Here's a phenyl group, and there are two of them, diphenyl, and they're attached to 9,10 on our anthracene molecule. The numbering on anthracene is pretty interesting. You go 1, 2, 3, 4, and then skip to 5, 6, 7, 8. That's because anthracene's based its numbering system on naphthalene, which goes through a logical 8, but when you toss in an extra one, their numbering system is weird, but that's organic chemistry. This is an interesting one in terms of it's very different. It's not very soluble in water. We list it as being insoluble, but again, there's so little anthracene, diphenylanthracene in here that doesn't matter if it's hardly soluble at all. But notice this doesn't have any OH groups or NH groups, no amines, no alcohols. It's just a group of our nonpolar benzene molecules. So this is really quite a different molecule from the other two. Let's see how this one compares to our others in this chromatography experiment. So here we've got our TLC plate, and we're putting a very, very small dot of each dye on the plate. You want to have the dots small enough so they don't blend into one another, but large enough so you can see them. Also notice that they're wearing some nitrile gloves because you don't want to use your fingertips on this because even the oils in your hand will mess this up. So here's our last solution, the mixture of everything together. They've got them on the plate and they're very carefully going to put them into our beaker that has the solution of ethanol and acetone. Ethanol and acetone eluent will soak up using capillary action, and here you'll see that little front moving up, and as it hits those dyes will dissolve in some of that ethanol acetone, but still at the same time be attracted to the back of that gel that's on the TLC plate. So we're witnessing this attraction between the less polar ethanol acetone solution and the fixed plates, very, very high polar hydrogen bonding of the silica gel. So here it comes all the way up to the top, and we'll stop right there. This is a beautiful experiment, but let's get to the science behind this. Here's a quote from Lord Kelvin of Kelvin temperature. When you can measure what you are speaking about and express it in numbers, you know something about it. When you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. So let's not make this a meager, unsatisfactory knowledge situation. Let's get a ruler in on this and do some measurement. And the first thing that we're going to measure is how far the solvent went. Everything is relevant to how the solvent moves. Now, once we've got the solvent, our next thing is to draw a line through the middle of each of the analytes' location. The middle is the easiest to measure. Trying to get the top and bottom is a bit more difficult. So the standard for making these other measurements is to go to the center of the dot that you see and estimate it as best you can. We've got our solvent, and we find that it is 6.0 centimeters on this ruler that I've put against TLC plate. The dye 1, the rhodamine B, which is orange, its center looks like it's pretty close to about 2.6, 2.65, but I think the best we can do is down to the nearest tenths. Dye 2, which is our rhodamine 6G, which is yellow, looks like it's about 4.9, and our dye 3, our anthracene, is all the way up to the top, but we have to use the center of it. That turns out to be most likely about 5.8. However, there's an extra color in there. You can see this green. This green is mixed in with rhodamine 6G. That 6G wasn't pure. There was inside of it an contamination. A green dye. Now, I've done a little bit of research on it. Most likely, this is a rhodamine 123. It's a pretty common dye. It's very, very similar in terms of molecular structure to the rhodamine 6G. It's missing 2 methyl groups, and it's a bit more polar. As a result, I think it would stick to the plate a little bit more often. So my guess is that unknown substance, this contamination, is rhodamine 123. So if this was a sample that they purchased, they probably should complain that their rhodamine 6G isn't pure 6G. This is one of the uses of chromatography, to find out if substances are pure or if there are impurities within the mixture. Well, let's follow Lord Kelvin's advice and take these measurements and make something out of it. The important factor here is called the RF. The retention factor, or more accurately, the solvent retention factor. It tells you how the analytes ended up sticking to the solvent rather than the TLC plate. And it's just a division of how far the analyte went compared to the solvent. So the solvent retention factor for the 1910 diphenyl anthracene, say that 5 times quickly, is 0.98, about as close as you can get. Of course, that was our least polar substance, and reinforces the fact that we would think that this substance with only LDFs would not be attracted at all to the very polar silica gel on the TCl plate. Our next substance, which is our rhodamine G, has a factor of 0.82, so we'd say that's probably a little bit more polar than the diphenyl anthracene. Rhodamine B, 0.43, even more polar because it stuck to that plate. And then, of course, our mystery green, which I'm pretty sure is rhodamine 123, our contamination, is the most polar of them all. So with this solvent retention factor, the lower the number, the more attracted it is to the fixed plate and its polarities. So this very, very simple experiment in terms of just putting some dots on and watching a solvent wash through a fixed media tells us about the actual structure of these molecules, and also can pick up these contaminations. This is really an amazing resource that chromatography is, and it's used in all sorts of fields. Well, let's watch this experiment again because it's really pretty.